Can you hear me okay? All right, let me just, so that's to forward. So before to begin, I'd like to ask the audience a question. How many of you here have worked at Intel for, you're going to have to raise your hand in one of these two questions because one of them has to be true. How many people have worked at Intel for 25 years or more? Wow, okay. How many have worked here for 25 years or less? All right. How many recognize what's on the screen here? Okay, it's a Jack in the Box just on the other side of 101, right? And I'm hoping that the people who have worked here for 25 years or more will validate my story because I have an interesting story to share with you. 1997, I was an undergraduate student at UC Berkeley, and I was working as an intern at SC9. I was a device engineer working on the first generation of Flash, eTalks. Under Simon Tam, we're reporting into Stefan Lai and so on. Those guys have all retired. And the story is that I've shared with other people. I was living in Berkeley. I grew up in the Bay Area, but going to Berkeley, I stayed there in the dorm, and working at Berkeley, running computer systems there in the early days of BSD, and then also getting an intern job at Intel. So I was driving every morning coming down here, and there was a rule that you had to be here before 9 o'clock, right? And Simon Tam told me this rule came directly from Andy Grove. And of course, coming from Berkeley, I had to get up at 4 or 5 o'clock to make sure that if there's any accidents or anything that I'd be here on time. And throughout the summer and then into the year, I'd be late several times. And when you're late, you have to sign up, at the lobby. And then one afternoon, Simon called me aside and said, "Hey, Christopher, I got to talk to you." And I said, "What's?" He looked very serious. And he said, I got a report that you've been here late more than 3 times. I was really surprised, and I thought maybe I'm just signing my name. And he said, "Actually, if you're here late more than 3 times, they report it to me, and I have to do something about it. And if I don't do something about it, somebody else higher is going to do something about it. And this has come directly from Andy." And then I said, "So what do I do? I mean, I'll get up at 1 o'clock in the morning." And then Simon said, No. This is what you do. If you get here and it's going to be after 9, drive over 101, go to this Jack in the Box, and stay there until 10, because they stopped collecting names after 10. I mean, how many people know this story? Right. So I did that, and sure enough, a week later, I had the need to do this, so I drove over to Jack in the Box, drove in there, 9:15 or something like that, saw a whole bunch of Intel badges in there. Okay, so I can end my talk now. But this has a bittersweet aspect to it. This was just 2 months ago. I had the opportunity to have a dinner at Ben Horowitz's house, honoring Andy, and of course we didn't know. And I was telling him this joke. I'm not going to tell you what he said, but I posted this on my Facebook page and said this is a very bittersweet opportunity to have had this dinner with him. And what I wrote was, he's the refugee from whom I learned semiconductor physics, strategy, leadership, and humanity. And I thought this is an appropriate place and time to have that acknowledgement. So with that, I'm Christopher Nguyen, co-founder and CEO of Arimo. And this is actually my 3rd startup, my 4th if you count the one that my wife really did, and I just helped out. And I've been an academic. I mentioned that I was undergrad at Berkeley, PhD Stanford. And I knew, because of people like Stefan Lai, Simon Tam, Andy Grove, I knew I was going to be a professor. And so I did. I became an ECE professor. There was a startup university in Hong Kong, the Hong Kong University of Science Technology. How many people know about that? So I started the computer engineering program there, and just recently gave a keynote at the 25th anniversary. So that's how old I am. But in between, so I realized I was a really more of an entrepreneur than a professor, and so I left and started 2 companies and sold both of them successfully before coming back to the US. And then Google was my reintegration in the Valley, and ended up running the operations team that ran Google Apps, Gmail, Calendar, Docs, and Spreadsheets, and so on. And I learned a lot about scale at Google. And in fact, a lot of the problem statements that we work on at Arimo today are from the lessons of scale that I learned there. I thought by the time I arrived at Google, I had learned everything, but it turns out there was a lot to be learned. This Arimo is sort of the most passionate startup, I would say, to date, and I hope the goal for Arimo is that the company will outlast my lifetime, taking the lessons of Andy Grove about S-curves in companies, lifetimes, and strategic inflection point. A lot of people don't know that the term inflection point came from Andy's book, Only the Paranoid Survives. So I'll go very quickly through what we do at Arimo. This is not an advertisement for the company, but it puts in context some of the technologies I'll be talking about. We build what we call a data intelligence platform, and it is a business user level application, but connecting them vertically all the way down through the web app system, the predictive engine, essentially the big compute layer, and all the way down to big data and coming back in just a few seconds. And so what we want people to be able to do, and we have already accomplished that, is to be able to go to their data systems and interact with what looks like a Google Docs application. I learned a lot about the value of collaboration in terms of different people with different skill sets coming into the same space and making decisions with the information available at their fingertips. And so that's what we've enabled. And maybe I'll just show you with 30 seconds that is actually a real application. And we're going to switch to, right? So it looks like my former Google Docs, but more beautiful even. And so these are what we call narratives, and they're dashboards. Customers love dashboards and data sets. And we would, how come my cursor is already there? Okay, so it looks like a very user-friendly document that you can type into it, right? We can, okay? And just with a single command, you can do things like forecast, right? Oh, what am I typing? I can't even see. And then arrival delay in the next 30 days of flight date, right? And this is all happening in real time. This is the only command I'll show you. There's a whole bunch of other stuff that you can do in natural language. But the idea is that it should be that accessible to the business user, right? All of the machine learning, all of the computing power that we are such experts at should really disappear, right? It's like the iPhone for machine learning. That's what it should be. And so, and that comes back, and you can, based on that, this is a very simple Holt-Winters forecasting algorithm, but you can see sort of 30 days into the future, right? And then make decisions based on that. So that's the idea of what we're building. So with that, let's switch back to the slide deck. We're good? All right. Next slide. Oh, that's my job, sorry. Okay, so the stack looks like this at a very high level. What we just saw is the business user looking down at the system, right? And at Google and consumer-oriented companies, this is what I learned, right? Prior to that, all my experience was enterprise. It's very much about looking at the world top-down or outside-in, right? As engineers, we tend to look at the world bottom-up and inside-out. But until you've built something that people can reach, there's 90% of the value that hasn't been realized. So the business user is looking at this narratives, and this is a series of web applications, and there's a predictive engine underneath that. And we built it such that we are essentially, in principle, engine agnostic. When I say engine, I mean both compute engine as well as data engine. Compute engines for us would be in-memory engines like Spark, Flink, Beam, and so on, right? And of course, today, the Hadoop ecosystem is so sophisticated that we can really pull data in from virtually any data source. We index very heavily on Spark. In fact, I want to claim my Spark creds by showing you, if you go to the Spark wiki page, You can see the first three editors, Andy Kowinski, Matej Zahari, and myself. So when we say we're the first company to bet on Spark commercially, we really are the first, right? So I want to quickly move to the near present. What we've done, in addition to all the other algorithms, one of the things that I personally have a lot of conviction in, and I'll talk about it more maybe during the panel session, is the power of deep learning. And I'm not exaggerating when I say I was telling Guok Lei, who was working on deep learning, that deep learning was going to be big, and he didn't realize it. That was a number of years ago. In November 2015, we talked about building distributed deep learning on Spark and Tachyon. Just this past February, I talked about essentially a similar architecture, but taking the single machine open source release by Google, TensorFlow, and then distributing it across a Spark cluster. And then in June, I don't know if this paper is in yet, but we'll be talking about TensorFlow ensembles, but also on the Spark infrastructure. And the motivation for doing this, sometimes people ask, you can do it using distributed TensorFlow without Spark. So why Spark, right? And then this is something that, again, you can also learn at large infrastructure companies like Google, is that if you already have a Spark implementation, right, like some of the enterprises do today, then the CIO wants to ask the question, can I put an additional workload on my existing investment, right? And that's a question that a lot of time engineers and PhDs forget. We're always going for the most optimal configuration singularly for a single problem without thinking about economies of scale. So that's the primary motivation for doing all of this stuff on Spark. And I'll go a little bit into the architecture of this. Some of you may recognize the architecture on the left-hand side as coming from the deep learning work at Google, right? Essentially, it's disbelief, Google and other places. But essentially, you can think, the easiest way to think about it is there are two major components in such a system. When it does gradient descent, there's some part that computes the gradients, and then the other part detects the gradient and update the parameters, and we call that the descent step. So the lower half there is the gradient computers, and above the parameter server there is the descent. So when we distributed that over Spark, well, essentially the Spark cluster, and how many people here are familiar with Spark? Good, okay. So you recognize these boxes immediately, and essentially what we do is we put TensorFlow on the driver and TensorFlow on every node, every worker as well. And essentially the communication between the two, the driver is the one that does the gradient, does the descent, and then there's a distributed computation of the next set of gradients. And of course, there's a lot of communication overheads and so on. And so in the paper, we talk about all of those trade-offs. Oops, okay, good. So this shows essentially, and this is almost like a preview, not a preview, an overview of the paper. I'm not going to go into great detail, but essentially we consider a number of architectural options. So it's not just we build this. So you can build a Spark-only distributed deep learning, and you can use the broadcast variable to shuffle the model back and forth. However large the model is, that's your broadcast variable. Tachyon, how many people here are familiar with Tachyon? Yeah, it's recently, well, you don't have to because it's recently renamed as well, so you can learn the new name, Alexio. I'm still calling it Tachyon. I can't get past it. So Tachyon is a distributed file system. So you can think of Tachyon as a storage for the model, right? It's memory speed. So we also look at an architecture where we're not actually broadcasting using the broadcast variable to pass the model around, but we do that in distributed manner using Tachyon. And the idea there is that Tachyon is only a memory server. And then you go to next. This is the third one is let me use the word traditional approach to having a parameter server in deep learning, and that parameter server typically communicates using HTTP. So that's a dedicated parameter server which we can distribute horizontally. And then the coolest thing of this whole architectural set of options is to use Tachyon not only as a storage for the model, but also to compute the update to the model. So that means that when Tachyon, as it is today, if you go to the Tachyon repository, you won't see this code yet, this co-processing code. But essentially, if we can put some compute capabilities in Tachyon, then it doesn't have to send the model back to another compute system to update the models. It can update the model after receiving the gradients. Does that make sense? Right, so that, it turns out, as you might expect, the highest performance in terms of convergence over time is on the rightmost hand side. And you can find that slide deck online. Okay, how much time do I have? Okay, there it is. I want to talk about the future of Spark. And I was careful not to put the IBM logo on here. But I think most of you know the Spark Technology Council, and I've been invited to set some of the agenda there. So in the last discussion, just to share with you what the discussion is, I talk about looking at Spark over the next 12 to 24 months, and the major challenge of that window and the major challenges of Spark in the 2 to 5 year time frame. And the 12 to 24 months is about enterprise adoption. That, from a lot of our perspective, is a key hurdle to get over. So if you look across the landscape today, if you look at Cloudera, MapR, Hortonworks, which essentially constitute most of the Hadoop market, there's about 2,800 to 3,000 Hadoop installations, plus or minus a few hundred, of which, by Arimo's definition, about 200 and 300 are mature. And by mature, we mean they are ready for a system like what I demoed to you. Essentially, if we talk to people that are not sufficiently mature in this case, and then they say, well, we're still busy just putting our Hadoop data lake or thinking about Hadoop strategy. And that's sort of one slice of the big data market. Of course, big data is much bigger than Hadoop, but Hadoop is one standard bearer. And then within that, there's a subset. We're talking about just dozens of Apache Spark installations. So the point of this slide is that even though, for a lot of us who live in this bubble of Silicon Valley, and you can't walk 10 feet without hearing Spark mentioned 3 times, for the most part, Spark is still very early in the enterprise adoption cycle, right? And when I go to the Midwest, maybe even the Northeast, and talk to customers, and they would say, yeah, we're thinking about doing Spark. What do you think about it, right? So that's where things are. So what are the challenges that, and this is what I share with the Spark Technology Council, is that, this is, if you want to help Spark, this is what we need to work on. So these are some of the key things that an enterprise CIO cares about. Robustness and reliability in Spark, right? Security as not just inherent in Spark, but security is as integrated with whatever the enterprise architecture currently has. Manageability, and I think that the biggest bullet of all that sort of catches everything is enterprise integration. It's those of us who work on Spark a lot would like Spark to take over the world and it's everything. But in fact, it's going to be one component that has to play well with everything else, not just the existing legacy stuff, but everything that will come in the future, right? 2 to 5 years, and the key thing about 2 to 5 years about Spark is that just like Hadoop has evolved, Hadoop in 2006 is very different from what Hadoop is in 2016. Spark will have to evolve, and I share a couple of directions or pressures for that evolution. One is above, from the application layer. Like people like us and applications like deep learning will have some evolutionary pressure on Spark. And then from below, the hardware architectural pressure. I'll skip through this quickly, but essentially, deep learning is going to be a key application architecture, right? And if Spark wants to play in that, and I think the answer has to be yes, there's going to be some re-architecturing or some additional support that's required, because Spark is fundamentally still very much a map-reduced paradigm, right? The second pressure is coming from the network. How many people here work on network data center fabric? I was exposed to a lot of this at Google. On the left-hand side is what Facebook has published recently in terms of the various communication planes in the fabric. Even that I consider traditional. People are now working on essentially direct point-to-point, right? Both optical as well as millimeter wave. Within 5 years, we're going to have an explosion in data center fabric by 1,000 times, right? In fabric in terms of total bandwidth. When you can have direct rack-to-rack communication, right, at full, the term full bisectional bandwidth will cease to have meaning because you can talk to anybody within the data center without any collision. And so when that happens, the paradigm of MapReduce, right? I tell people, who grew up in the MapReduce era thinking that that is the pattern for parallel computing. I said, no, it's actually one of 13, right? How many people are familiar with the 7 dwarfs, the 13 dwarfs of parallel computing, right? You gotta read this paper. It's like puts everything in perspective. It comes from Phil Colella at Lawrence Berkeley Lab, and he was working on distributed processing, and then he was looking at communication patterns across all his nodes, and he said, I'm looking at these things, and there seem to be 7 patterns. And it was a single slide, and he can't even find the slide. I talked to him. But Dave Patterson was in the audience. He said, well, this is really interesting. So Dave went back to Berkeley and then talked to graphics people, machine learning people, and one other group, I forget. But they came up with 13 dwarfs. And so you should look up this paper. But essentially, MapReduce is for the era where compute is cheap and communication is very expensive in relation to that. But imagine when you go to move to an era where, and the bottleneck always changes, right? It always switches every few years. When communication becomes cheap, there will be more and more pressure to use that bandwidth. And so there will be more graph computation, full graph computation will begin to make more and more sense. And Spark today is not at the fundamental core designed for that kind of message passing paradigm. Oops, why did I go back? Okay. So essentially, then this sort of ends my talk. If Tachyon today is memory speed file system, I'm actually convinced that Tachyon or something like it is going to be, the noun and the adjective is going to change. It's going to be a file system back shared memory. I talked to Hao Yuan about this, and when he thinks about building Alluxio, should take this into account. What will become of Spark, right? If Spark wants to become relevant, it has to anticipate these things, or something else will come and take over that umbrella. Okay, so why do I think about things like this? In the context of building Arimo, we want essentially, as a company, I started out at the top of the talk, we want Arimo to outlast my own lifetime. And so today we are somewhere between inferential and predictive in terms of applications of machine learning, machine intelligence. We're going to get to the prescriptive phase, and I look forward to a day when my mind is wired to the machine. Absolutely going to happen without a doubt, and it's going to be very exciting. And I want Arimo to be at the forefront of that every single step of the way. Thank you.